Hello, and welcome back to the course. Today we're going to look at convergence of sequences of holomorphic functions. So this is section of subsection 3.4.2 in the book. So the question is, what is the right topology? What is the right notion of convergence for holomorphic functions? So as an analyst, if you're given a new class of functions, such as holomorphic functions, one of the first things that you should ask for is, how should we take limits of these functions? What's the right topology there? What's the right notion of convergence? So, curiously, for holomorphic functions, this is actually the same topology, the right one, as for continuous functions. And this is weird because there's way more continuous functions than holomorphic functions. Continuous functions can be really, really wild, while holomorphic functions are fairly rigid, very special, right? There's way more continuous functions. So the right topology is uniform convergence on compact subsets. So basically, we have a sequence of functions f sub n, and a function f on some set u. Suppose that this u is a subset of the complex plane. Then we have uniform convergence of compact subsets if for every compact set k that is a subset of u, right? We have that the restrictions of this sequence of functions, so f sub n restricted to k, that converges uniformly to f restricted to k. So we don't quite get uniform convergence, but on every compact set we have uniform convergence. So this is slightly more general than uniform convergence, and you can generally take if U is a subset of the complex plane, you can exhaust it by compact sets on which you can then have uniform convergence. Basically, we have U is sort of locally compact, right? I mean, you can have every point has a compact neighborhood, so we really get uniform convergence in every neighborhood. All right. So what do we mean by the right topology? And so one of the things that we want is for the topology for this convergence, for this notion of convergence, to preserve our space of functions. So if we have if our space of functions, for example, the holomorphic function, so if all the fn's are holomorphic, then if this sequence converges to some f in this way, namely in this setting uniformly in compact subsets, then we'd want f to be holomorphic. We don't want to go out of our space, right? So that's, it's one of the most basic requirements. There's, of course, more that we want. We want this to really be sort of a natural one. Hopefully, one that arises in a lot of problems that where holomorphic functions arise. And actually, we've already seen this convergence, if you remember, for power series. So this is a fairly natural notion of convergence for holomorphic functions. Now, it also is the natural convergence for continuous functions, because uniform convergence of continuous functions gives us continuous functions, and since we have, that's only necessary in every neighborhood. So if you have compact neighborhoods, right, you just take a little compact disk around every point. So if I have a sequence of continuous functions and it converges uniformly on compact subsets, then it converges uniformly on every one of those disks. So it's continuous in every disk, therefore it's continuous everywhere because continuity is a local notion. And really the same idea is true for holomorphic functions. Right. But for real differential functions, so actually something that's in between continuous functions and holomorphic functions, right? Something that's slightly, there's fewer differentiable functions, right? It's a stronger requirement, but real differentiable functions is just functions with real derivatives. But there's way more of them than holomorphic functions. And its uniform convergence is not good enough there. So for example, if I take this sequence, and we can really just look in the, let's say, the interval -1 to 1 or something, then this sequence converges uniformly, the absolute value of x, right? So we're now just working on R rather than C. You could make this work on C if you wanted to. So we take the absolute value of x, and we take it to the 1 plus 1 over n. So it's just something slightly bigger than the first power, right? And we're taking this n going to infinity, so the power is getting smaller and smaller and smaller. That converges uniformly on really any bounded interval to absolute value x. And something that you notice about absolute value of x, it is not differentiable at the origin, while this guy, maybe it takes a little bit of a little bit of thinking, but that guy has a derivative, and actually the derivative is continuous. So that's a nice differentiable, continuously differentiable function. So yeah. So this is not true for differentiable function, continuously differentiable functions, whatever. It's true for continuous functions, so really, really wild functions. Then, you make these functions nicer. So for a while, it doesn't work, and suddenly it works for holomorphic functions. It's kind of weird. All right. So what do we get? So this is the term that we'll prove. So suppose that we have an open subset of the complex plane. We have a sequence of holomorphic functions converging uniformly on compact subsets to some function f, defined in U, right? So what's the first conclusion? The first bit of it is that f is holomorphic, right? So that's what we were talking about. It is sort of the right notion of convergence, but actually we get more. It's really, really the right notion of convergence, because what we get is that for every natural number L, so 1, 2, 3, 4, 5, etc., the Lth derivative, which we denote by f sub n to the L in parentheses, that guy converges uniformly on compact subsets, and not just to anything, it converges to the Lth derivative of f. Now that's a little weird, because I'm only asking for convergence of the function itself, and I get convergence of all the derivatives automatically. It's given to me, right? Now, for real differential function, if we take, for example, real smooth functions that have infinitely many derivatives, but just the real derivatives, if the right convergence over there would be that all the derivatives converge, right? And that would give you smooth functions, and all the derivatives converge uniformly on compact subsets, something like that. That would give you the right sort of convergence over there. Over here, we're only asking for the function to converge uniformly in compact subsets, and we automatically get that all the derivatives converge, right? So, yeah, it's very strong, right? So, and if you'd ask for all the derivatives to converge as well in the same sense, well, you're getting the same concept of convergence actually, right? Kind of weirdly. All right, so let's fix a point P, and let's consider a little disk. So fix a point and consider a little disk around P, right? A little closed disk. And suppose that the whole closed disk is in U, right? So including the boundary, that's important. That's supposed to be a subset of U. Now, for any Z inside this disk, we do have Cauchy's formula, right? So this thing is true, right? So if I take a Z, any Z, that's true. So fix that Z for a moment, right? Now, if I look at the boundary of this disk, the boundary of this disk is a compact set, right? It's the little circle around. It's a closed bounded set, and it's a subset of U. So it's a compact subset of U, right? Now Z is inside the disk, so I can take the distance from Z to the circle, right? I mean, the Z is not necessarily in the center, right? This is the center, maybe Z is over here, but it's still some positive distance away from the boundary, right? So let delta be that distance. All right, now if I take any zeta, and it's going to really be, right, I'm integrating over the circle, right? So it's going to be that zeta, right? So for any zeta in this circle, I look at I'm looking at how the inside converges, right? For a fixed Z, right? So I look at the f sub n of zeta divided by zeta minus Z, so the integrand over here, and I look at what the limit would be, right? And I just I take the absolute value. So what's the size of this, right? And we're really sort of fixing Z. So we just write it like this, right? That's just a little bit of algebra. And well, now we can estimate it because we know that at Z, the distance to the circle is delta, right? So that's the shortest distance, right? Shortest difference between, so the smallest that zeta minus Z is, I get this estimate, right? I can bound it by 1 over delta, right? Because that's the biggest 1 over zeta minus Z can be, times the distance between Fn and F. Now, what's the point of this of this estimate? This estimate says that for a fixed Z, this function of zeta, right? So the integrand as a function of zeta converges uniformly to the integrand with if we put an f in there, right, on the circle. Why? Well, it does that because this goes to 0 uniformly, right? Because we do have this guy is compact, and we have that Fn goes uniformly on compact subsets to F. All right. So what does that mean? That means we have uniform convergence in the integral, right? This is really just really just a Riemann integral, right? And we know that if we have uniform limits, we can pass them inside, right? So we can take the limit in n, right? So we can take it on this side, and we can take it on this side, and on this side, on the right-hand side, we can just take the limit inside out here, right? And we get it's the same thing, right? So what do we get? We get that once we take the limit, that we get this sort of formula. We get basically the Cauchy formula on this disk for F, right? And this worked for any z, right? So it didn't have to be just, that particular z. Yeah, it's, once you took that limit, that worked for any z. Now, a little bit of technicality. Now, it's f itself is a continuous function. It converges uniformly in compact subsets continuous, right? But namely here, what would be important is that f restricted to the boundary to the circle is continuous, again, by uniform convergence. So what we can say, something that we proved before last time, is that the Cauchy transform, for which we needed, for that proof, we needed a continuous function, necessarily a continuous function, but the way that we proved it, with a continuous function. So the Cauchy transform of a continuous function on the boundary is holomorphic inside. Well, what did we just prove? We proved that the function inside is equal to the Cauchy transform. Now, the Cauchy transform, we proved, is holomorphic. Right. So therefore, f is holomorphic in the disk, and therefore f is holomorphic. Holomorphicity is a local thing. Once I have holomorphicity in every little disk, I have it everywhere, right? Okay. So we have that f is holomorphic, right? So we're sort of halfway there. It's the first thing that we wanted. We still need that moreover bit, right? We need that all the derivatives also converge uniformly on compact subsets. All right, so let's do that. Suppose that that K is a compact subset of U, right? And we have to be it's a little bit of a technicality, but if U is not all of C, let D be the distance between K and the boundary of U. K is compact, boundary of U is closed. There is some some distance, right? Some positive distance. Now, if U is all of C, there is no boundary of U. Just take an arbitrary number D, 5, 10, 20, doesn't really matter, right? And now let's construct this new set, K prime. And what do? We take the union of all closed disks of radius half of D, right? So, and for all points in K. So you basically fatten up K a little bit. Now, what I claim is that this K prime, this sort of fatter K, is still compact and is still a subset of U. That it's a subset of U is fairly easy, right? Because D is the distance from K to the boundary, right? So if I only go D over 2 away, I can't be at the boundary yet, right? I still have to be inside U. So all of these disks are inside U, and therefore K prime is inside U. It's to still prove that it's compact, right? Now it's bounded. Well, that's not hard to see because K is compact, therefore it's bounded, and I'm just making something, D over 2 bigger, right? So whatever the bound would be for K, just add D over 2 to it, and you have the bound for K prime. So K prime is bounded. It's proved that it's closed. So it's closed, complement is open, right? So let's suppose that P is in the complement, right? So P is some point in the complement. I have to show that there's a whole neighborhood around P which is not in K prime. All right. So there exists some Q in K, right? In K, not K prime, K, such that P minus Q, the distance between P and Q, is the distance between K and P, right? There's a point Q in K that is closest to P. That is because K is compact. Like, we can do that. right? Now, because P is not in K prime, right? We have that this distance must be bigger than d over 2, right? Because if it was less than or equal to, then we would be in one of these disks, right? And we're not, right? We're not in K prime. All right. So then if I take, right, so what does this mean? That means I can subtract d over 2 from p minus q and still get a positive number. So we can take a look at this and this disk, right? Now, every one of those points, right, is further than d over 2 from k. I mean, it's just by triangle inequality. So therefore, it cannot be in K prime, right? So this entire disk is not in K prime, and therefore K prime is bounded. K prime is closed. And so therefore it's compact because it's bounded and closed, and it's a subset of the complex plane. It's closed as a subset of the complex plane and bounded, therefore compact, right? And there's always someone that thinks that closed and bounded is the same as compact. It's not true. Compact sets are closed and bounded, and sets in Euclidean space, such as C, that are bounded and closed in the Euclidean space, not in some subspace topology or something like that, those are compact. Again, and that Euclidean space had better be finite dimensional, right? So that's the only place where you can say that. Anyway, it is in this case we are a closed and bounded subset of C, so it's compact. All right, we have this compact subset. We have that the sequence converges uniformly on K prime because, well, I mean, it's a compact subset of U, right? In particular, not just a compact subset of C, it's a compact subset of U. And so therefore, we have that the sequence converged uniformly in compact subsets. It converges uniformly on K prime. So given any epsilon, any positive epsilon, there exists an n, as I said, for all little n bigger than capital N, and all z in that compact subset K prime, we have that the difference between f and f sub n is less than epsilon, right? I mean, this is definition of uniform convergence, right? So now we apply, so for any p in K, so now we look at just K, right? So we have uniform convergence on K prime, but now we look at points in K, and we apply the Cauchy estimates on one of these disks, right? Which is going to be a subset of K prime where we do have uniform convergence, right? And we look at the difference between the nth the Lth derivative of the nth function and the Lth derivative of the limit function, right? We want that to be bounded by something that's uniform over K, right? And so now we apply the Cauchy estimate to this because that's a holomorphic function, right? So we apply, right? And I mean, we really apply it to this guy, right? And we get that, well, there's this L factorial and d over 2 to the L, right? Because we're applying it in this disk, but d and L are just constants. Who cares about them? the thing is, it's bounded by some constant times the uniform distance, the uniform norm of f minus fn on this circle, right? Which is a subset of k prime, and we have this estimate. Therefore, I can bound this guy by epsilon, and if I rewrite the rest a little bit, I get some constant times epsilon. Well, that constant doesn't really matter, right? I can make epsilon arbitrarily small. Therefore, f sub n, Lth derivative of f sub n converges uniformly to the Lth derivative of f on k, right? So now the key point here is that we fattened things up, and we used the uniform convergence in the fatter compact set to get uniform convergence in the smaller compact set. That's actually something that comes up quite often, this sort of idea, and it's really because of the Cauchy formula that, right? I mean, Cauchy formula comes in here, right? So the point is, you can write derivatives of f as integrals of f. And integrals are far nicer. I mean, unless you ask a calculus student, then they won't agree with you. But integrals are much, much nicer than derivatives. Derivatives are terrible. Integrals, you can integrate almost anything, right? You just, not in calculus, not in closed form or whatever, but we don't care about that. We only, you can integrate any continuous function, right? It's a nice thing, right? It's easy to integrate. It's easy to get estimates from integration. It's much harder to get something from differentiation. But for holomorphic functions, differentiation is integration. We can, well, in some sense, right? We can bound derivatives by the integrals, right? So that's the key thing in this proof. All right. So that's it for today. So next time we're gonna look at Schwarz's lemma. So see you next time.